In section 6.2, we're going to look at multiplying and dividing radical expression. The first thing we're going to look at is the property for multiplying and dividing radical expressions, which basically tells us that we have an nth root of a and the nth root of b. And when we multiply those, we're just going to get the nth root of a times b. The key thing here is that the indices are the same. You notice that there's an n for both of those indices. So when we multiply those radicals, we're going to multiply the coefficients, which will be typically sitting here. We'll multiply the radicands, which will be sitting in here. And of course, only way that's possible is if this index that's right here is the same for both of them. And then of course, we'll simplify if possible. So let's look at a specific example. Here we have the square root of 5 times the square root of 7. Of course, my index for both of those is an understood 2, so I can multiply that. That's going to give me the square root of 35. That is not reducible, so I am finished. Moving on to the next example here, I notice that my index for both of those is a 5, so I can multiply. So I will multiply the coefficient. 2 times 3 is 6. That's going to be times the 5th root of, and then I will multiply the radicand. 4 times 8 is 32. Now, if I've got my chart in front of me that I've been using, I'm going to refer to that, and I'm going to notice that I can take the 5th root of 32. That's just 2. So this is 6 times 2 is 12. Finally, looking at the last example, again, I can do the multiplication because my index for both of them is a 3. So I'll multiply the coefficient, negative 8, and then that's times the square root of, and then I'll multiply my radicands here. And when I do that, I'm going to get an 8, x to the 6th, y to the 3rd. Okay? I will simplify that if possible, and drawing on our knowledge from the last lesson, I remember that I'm simply going to, oops, I forgot something. Need a cube root here. So I'm going to simply look to see, can I take the cube root of 8? And I can. When I do, I get a 2. So that's a negative 8 times 2, which is a negative 16. And then remember that when I pull this x to the 6 out, I'm simply dividing that exponent. So it's going to be 6 divided by 3 is 2, and 3 divided by 3 is an understood 1. So my answer here is a negative 16x squared y. So can we simplify this particular product here? And hopefully, when you look at that, you will see that the answer is no, we cannot, because my index is not the same. So that cannot be simplified. So now we're going to use that property of multiplication sort of in a reverse fashion to help us simplify a radical that otherwise would not be able to be simplified. In other words, I don't have a perfect square for 8. But what I can do is rewrite it as the product of 4 and 2. And I do have a perfect square for 4. That's just 2. So I'll rewrite this as the square root of 4 times the square root of 2, simply splitting it up. So you can see we're using that property of multiplication backwards in order to reduce our radicals. When I look down here at the cube root of 250, I need to think to myself, is 250 a perfect cube? So I would look in my list and I would find that it is not a perfect cube. Then I would think, is it divisible by a perfect cube? And hopefully I would see that it is. It's divisible by 125. So I can rewrite that as 125 times 2. And I can take the cube root of 125. It is simply 5. So I have 5 on the cube root of 2 as my answer. And then finally, looking at this last example here, I have the 4th root of 32. I would look in my list of 4th roots to see if, or 4th powers, to see if 32 is there. And I would see that it is not there. I do not have a 32, any number that can be raised to a 4th power and get 32. But it is divisible by 1. It's divisible by 16. So I'm going to rewrite this as 16 times 2. I'm simply taking the 4th root of 62. That is 2 on the 4th root of 2. Okay, so we're going to move to a pretty complicated problem here, and we're just going to start off by multiplying. And when we do, we're going to, first of all, we have to check to make sure that our index is the same for both of them, and it is. It's an understood 2, so I'll go ahead and do that multiplication. It's 1,575, x to the 6th, y to the 7th. Now what I want to do here is I want to simplify that radical as much as possible. So I'm dealing with a square root here, so I'm thinking of things that are perfect squares. Well, 1,575 is not a perfect square, but it is divisible by 1. You may immediately think it's divisible by 25, and you're right, it is. However, we want to choose the one that is the largest that will go into it. And if you keep looking in your list, you would find that 225 will also go into 1,575. 225 times 7. All right, let's look at these numbers. These variables. If I look at this x to the 6th, that is something that when I reduce this away, 6 divided by 2, that will go nicely. So I'm just going to rewrite this. But the 7 is not. I can't divide 7 by 2. So what I'm going to do is sort of a little cheat. I'm going to break that y to the 7th up into y to the 6th times y to the 1st. And you see now what I have are things that I can take the square root of. So let's do that. The square root of 225 is 15. The square root of x to the 6th is x cubed. The square root of y to the 6th is y cubed. And left underneath I have 7y, and that is my final answer. So now that we've looked at multiplying and we feel hopefully fairly confident with how to multiply, we're going to look at dividing. And again, the key thing is going to be here that our index is the same. And then if possible, if that is the same, we will divide the radicands. And then we're going to note that if it's not the same, we will rationalize the denominator. We do not want to leave a radical in the denominator. Okay, so if we look at this particular example, you can see these are square roots, so I could theoretically do this division, except that I can't. 6 divided by 7 won't reduce. So what I'm going to do is rationalize the denominator. Alright, so what I'm essentially going to do is take that square root of 6 over the square root of 7 and multiply it by something so that I end up with a perfect square. Now the key is I want that perfect square in the denominator because it's the denominator that I don't want the radical in. So think about it. If I multiply by a square root of 7, that's going to give me the square root of 49 on the bottom, which of course is fine. Okay, but I can't just multiply it by anything, so what I'm actually going to do is multiply by the square root of 7 over the square root of 7. Okay, so if you look at that, I'm technically multiplying by 1. And multiplying by 1 is fine. That will simply change my form and not change the value. So now doing this multiplication across, I get the square root of 42 over the square root of 49. Simplifying one more time, this is the square root of 42 over 7. Okay, so what about here? Well, again, check my indices. Can I divide? The answer is yes. Actually, if you look at this one's a little easier than the last one. We actually can do this division. 189 is divisible by 7, and when you do that, you get 27. And, oops, it's a cube root. And then remember for variables, we're simply, if the bases are the same, we simply subtract the exponents. So this is cube root of 27 x to the 5th. Now, I do want to simplify that if possible, and it turns out I can take the cube root of 27. That's just a 3. And then I can rewrite that x to the 5th as x cubed times x squared. Well, think about why I would want to do that. If I do that, then I'm creating this piece or fixing this piece so I can pull it out because it's divisible by that 3. And all the stuff that's not, I'm just kind of leaving it in the leftover pile here, if you will. So this is 3x, because 3 divided by 3 is 1, on the cube root of x squared. And that is my final answer. Okay, so just quickly looking through this one where the example has already worked for us, just want to point out a couple things. So you can see here I have 3 over the square root of 12. Okay, but the square root of 12 and the 3 is not under a radical, so I certainly cannot do this division. So what I'm going to do instead is rationalize my denominator. So you may ask, why did you multiply by the square root of 3? Well, think about it. What do I need to multiply 12 by to make it become something that will be a perfect square? Well, look in your list of perfect squares. 36 is hanging out there, and 12 times 3 gives me 36. So you can see that's what I've done. Now, when I take the square root of 36, I just get a 6, and this has a mistake on it. This should actually be the square root of 3 over 2. Really important that I cannot reduce at any of the steps before this one right here, and that is because this is under a radical. This is under a radical, and this one is not. Okay, so let's look at just a couple more examples here. I'm going to try to reduce that if possible. I'm going to check to see, is my index the same? And it is. So can I divide 56 by 7? And the answer, of course, is yes. X to the 5th divided by x is just x to the 4th. Y to the 5th divided by y is just y to the 4th. And it looks to me like I can do quite a bit of damage reducing this guy. 8 is not a perfect square, but it is divisible by 1. I can rewrite that as 4 times 2. And then simply pulling out, square root of 4 is 2. The square root of x to the 4th is x squared. And the square root of y to the 4th is y squared. Now, this cannot come out, so I'm going to leave it under my radical. And my answer is right here, 2x squared y squared on the square root of 2. Okay, so let's look at this guy. When you look at it, the first thing you want to notice is that your index is the same. You can simplify this, but look at it. You can't do anything with that. This is a 7 and a 5, an x and a y, nothing you can do. But we cannot leave a radical in the denominator. So, in order to fix the radical in the denominator, what I'm going to do is I'm going to multiply by something, just like I've done in the previous problems. But I'm going to think about what it is I need to multiply by. Okay, so I'm multiplying by what? Well, keeping in mind that it is the denominator I want to fix. That's the denominator that I'm going to look at to decide what to multiply by. Well, I know I have to have a cube root, because otherwise I can't do the multiplication. I need to multiply by something so that I get a perfect cube. Well, I can go through my list and figure it out, and I think I could probably do that fairly quickly with this example. But I want to just think about this for a second. What if I just multiplied by 5 squared? That would be 5 to the 1st times 5 squared would certainly be 5 cubed, and I certainly can take the cube root of that. In the same kind of way, I'm just going to multiply by a y there. And of course, I'm going to keep my numerator the exact same so that I'm multiplying by, ultimately by 1, so that I change my form and not the value. Okay, so in the top, can't really do much to that. I'm simply going to do that multiplication. And notice that this is 25 already. So I'm going to say I get the cube root of 7 times 25 is 175. And that's xy over. And I'm going to have the cube root of 5 cubed y cubed. And this I can completely simplify, and I get the cube root 175xy over 5y. And that's my answer. Okay, one last problem. Here we go. First thing I'm going to do is look to see, are my indices the same so that I can reduce? And yes, they are. They're both a 3. And so I'm going to start off by trying to reduce this fraction. So I'm going to have the cube root of, 48 divided by 6 is 8. All right. Now, look at those x's. I have more x's in the bottom than the top. So when I subtract those exponents, they're going to land in the bottom. And when I subtract the exponents on the y, they're going to land in the top. You can see, because I have more y's in the top. So now I need to rationalize that denominator. So I'm going to multiply by the square, sorry, not the square root, that won't work. The cube root of something. Okay, I need something that will create for myself a perfect cube. So I already have 1x. I need to multiply by 2 more x's. And so that creates for me the cube root of 8x squared y over, and in the bottom, the cube root of x cubed. But I can take the cube root of x cubed. That's just going to give me the cube root of x squared y over x. Okay, and I worked all that way and just realized that I can take the cube root of 8 also. Forgot to do that. So this is 2 on the cube root of x squared y all over x. And that is my final answer. Good luck on your classwork tomorrow, and I will be back soon to help you.